So we have defined matrix-matrix multiplication for the general case where the matrices A, B, and C have some number of rows and columns. What we're going to focus on now are special cases of matrix-matrix multiplication that themselves are interesting operations. As a matter of fact, many of them you've seen before. You've been playing around with IPython notebooks and with Python. One thing that you should have noticed that when we use NumPy, we tend to make everything a matrix. Often a scalar we just create as a 1-by-1 matrix. A vector we create as a matrix with one column. A row vector we create as a matrix with one row, and so forth. What we're going to do now is we're going to look at matrix-matrix multiplication, and we're going to see that when we're working with one of those special shapes, exactly the same operation comes out as we have seen before. Let's have a look. Remember that we're always looking at a matrix-matrix multiply that looks like this. Now, what if we take this size to be 1, and this size to be 1, and this inner dimension to be 1? That's the case where m is equal to n is equal to k is equal to 1. What you end up with is a 1-by-1 matrix being computed by multiplying a 1-by-1 matrix times a 1-by-1 matrix. But what is that? Well, that's just a scalar times a scalar by our definition of matrix-matrix multiply. Because remember, the 0, 0 entry in C has to be computed as the dot product of the 0th row of A with the 0th column of B. The 0th row of A only has one element in it. The 0th column of B only has one element in it. And therefore you just end up with this scalar multiplication. So, you can now forget about scalar multiplication. You just remember how to do a matrix-matrix multiply, and the scalar multiplication is just a special case of that. Well, what about the case where m is some size, but the n dimension and the k dimension are equal to 1? Well, then you end up with this special case. And what do we have? We have a column vector being computed as a column vector times a scalar. Well, what does that look like? It looks like this. And if you look at a typical entry in your column vector, but you consider it to be a matrix, you know that you have to compute that as the dot product of that row times the corresponding column of B. But notice that again, that row only has one element in it, that column only has one element in it, and therefore each of the entries in the column is simply computed with a scalar multiplication of the corresponding element in matrix A, or in this case, or vector A, whatever you want to call it, with the matrix B, but B is just a scalar. Now, we haven't actually seen this operation before, because this would be the operation A times beta, where A is a vector. What we have seen is beta times A, and it's interesting to note that that gives one and the same result. What if we have the case where m is 1, which means C only has one row, and A only has one row, and k is equal to 1, which means that A only has one column, and B has only one row? Well, let's have a look. A typical entry in matrix C, which is now a row vector, is computed as the corresponding row inner product with the corresponding column of B. Okay, but if you look at that corresponding column of B, all that happens then is that you take that scalar that is matrix A times the entry in B. So, this is very much like a scalar times a vector, except that the vector happens to be a row vector. What about the case where m is 1 and n is 1? Well, then A only has one row and B only has one column. But we've seen that as the dot product. And we know how to compute the dot product, but let's think of it from a matrix point of view. We have a 1-by-1 matrix, and that entry in the matrix is computed by taking the dot product of the corresponding row with the corresponding column. And that's just the dot product as we know it. So, the dot product is just a special case of matrix-matrix multiplication. Now this one is a little trickier. It's known as the outer product. Okay? Remember that the dot product was known as the inner product, it is not the same as the outer product. And you're going to make this mistake, and it will be on your exam. What is the outer product? Well, you take a column vector, and you multiply it times a row vector. If you want to determine what the size of the resulting matrix is, it has to have as many rows as A has rows, and as many columns as B has columns. So that tells you that you don't end up with a scalar as a result as you would for an inner product or dot product. Instead, you end up with a matrix. How is that matrix computed? Well, to compute a typical entry, you have to do a dot product of the corresponding row with the corresponding column. This dot product involves a row with only one entry and a column with only one entry. And if you look at it, that means that you simply do a scalar multiplication of those two elements to come up with the resulting element in matrix C. Okay, well, here's another one we've seen before. If n is equal to 1, then C has only one column and B has only one column. And lo and behold, we end up with a matrix vector multiplication. But when you look at how a matrix vector multiplication is computed, it's computed as the row corresponding to the element entry that you're trying to compute, dot product with the vector. That's exactly how matrix vector multiplication was defined. So whether you view these as matrices or you view them as matrix A and vectors C and B, you get exactly the same result. And finally, you have the special case where you're trying to compute a row vector by multiplying a row vector times a matrix. So that's the case where m is equal to 1. And if you compute that, again, a typical entry in the row that you're trying to compute is computed as the dot product of the corresponding row. There's only one row, and with the corresponding column. All vector-vector and matrix-vector operations that we've seen before are just special cases of matrix-matrix multiplication. So you don't have to remember everything we taught you in the first 3 weeks of the course. You just have to remember how to do a matrix-matrix multiply. Well, not really, right? Because we're going to be layering. We already saw how matrix-matrix multiplication can be thought of as matrix vector multiplication with the individual columns. And we're going to use and abuse that as we design algorithms for computing matrix-matrix multiplication, and also as we go forward with the theory of linear algebra.